I'm Hermine Maas, and I'm going to co-lead the session on Univariate twin modeling 7 ways with Elizabeth Prom-Wormley. This presentation is based on a 2020 session in the twin workshop held in Boulder, Colorado, and led by Sarah Medland, Lucia Colotro Conde, and Jose Morosoli Garcia. It builds on previous presentations, which were recorded by Michael Neal and Connor Dolan, covering an intro to structure equation modeling, as well as likelihood, and genetically informative designs. The rationale for this session is to understand the causes of variation in a phenotype of interest and partitioning this variation in genetic and environmental variance components. Now, this can be done in a variety of ways, and the traditional one is using genetically informative designs, which allow you to estimate twin heritability by inferring genetic and environmental contributions to variance from phenotypic covariances or correlations among family members, often twins, using their expected relatedness. We will build on this design and extend it by adding additional relatives and incorporating their actual relatedness, and thus moving into genomically informative designs that infer genetic and environmental contributions to variance from genetic relationship matrices or correlations based on measured genotypes of individuals. And this is often referred to as SNP heritability, of which you'll hear a lot more in later sessions. So a quick outline of this session. We will start from the basic twin model for monozygotic and dizygotic twins. And for those of you who have little background in twin modeling, we have generated some additional videos on univariate twin modeling in Openmx, again based on the 2020 workshop session that has an intro to the classical twin study design, as well as how to fit both saturated and twin models in Openmx to estimate means, covariances, and variance components, and a quick introduction into the differences between the path and the variance estimation approach. Here today, we will take that original twin model and then extend it in a variety of ways, and also show that it can be parameterized in alternate ways. So the key of these models is really in the variance covariance matrices. So that's what we are going to focus on primarily. You can find the files for this session in my faculty drive, and here they're labeled according to the key feature of each of these 7 scripts that we will be discussing. They all start with 1 ACEVC, which stands for 1 phenotype. We're fitting an ACE model using a variance components approach, and we'll use continuous data. Before we get started, a few Openmx details. Of course, you can find more information on the Openmx website. It's important to recognize that Openmx has a very fluid and flexible structure. And the way we like to write scripts is by creating code snippets that are saved as objects. It's important to remember that these objects and the names of these objects are often reused across scripts, but may mean different things. So it's important to keep that in mind. There are very few reserved names, and it's important it's very flexible, so you can name a matrix whatever you like. It's also important to recognize that projects also contain the data, so they can become quite large. Now, as indicated by Mike Neal's presentation, Openmx, which builds on classic MX, is really built around matrices. Matrices are the building blocks, so it's important to know how we put numbers into matrices and get estimates out of matrices. So a critical command is the mx matrix command. Matrices can come in a variety of types, of course, have dimensions indicated by their number of rows and columns, and their elements can be either fixed values or parameters that are going to be estimated in the model. We can provide start values and labels and names, and it's important to recognize the difference between the name given to a matrix within an MX matrix statement, which can then later be used in MX algebra statements, and the name of the object that this matrix is saved in, which is incorporated in the MX model to be able to manipulate the various elements of that matrix. Rather than using real data here, we are using a simulated data set of about 2,000 pairs of twins, where we've also simulated an extra full sibling. So the variables in the data set that we'll be using with are the actual phenotypes that we generated, called twin 1, twin 2, or SIB, the ages as well as the sex of the siblings. We assigned zygosity as 1 for MZ or 2 for DZ, and created additional variables for their expected relatedness, which we call rel-T for twins, which is 1 or a half, depending on whether they're MZ or DZ, and rel-S for siblings, which is 0.5. Then we also have genomic relatedness simulated, and so we indicate that by rel-1,2 as the relationship between twin 1 and twin 2, 1,3 between twin 1 and SIB, and 2,3 between twin 2 and SIB. So this is what an actual data set looks like. And here the data set includes about 1,000 MZ twin pairs, which are at the top of the file, and at the bottom are the DC twins. And you can see the difference in both their rel-T values as well in the rel-1,2, which is the expected relationship for twins, which is 1 for MZs and around 0.5 for DZs, on average 0.5 for DZs. Now, a quick note on the notation of the variance components, because these are sometimes used interchangeably. So we refer to V as the phenotypic variance that we are going to compose into any of the following sources of variance, including A, the additive genetic variance, C, the common or shared environmental variance, E, the unique environmental variance, or D, the dominance genetic variance. And we'll often also talk about the concept of heritability, which really expresses the genetic variance as a function of the total variance. So we get a proportion of the variance accounted for by genetic factors, either by additive and dominance factors combined as the broad heritability, or just the additive genetic factors referred to as the narrow heritability. So let's start with our first script. And for those of you familiar with fitting twin models in Openmx, this should be very straightforward. We'll provide just the basics here, but refer those with less background to the videos to get a more thorough description of how to fit a twin model in Openmx. So this is what the basic ACE model looks in terms of a path diagram, which we can then translate into expected variances and covariances using the rules of path analysis explained earlier. So the idea is here to use data from the relationships between members of MZs and DZ twin pairs to infer the role of genes and environment, in this case, operationalized as A, C, and E. Now, a quick sidestep into what an Openmx script looks like. We're not going to describe every line of scripts in detail, but just show you here how a typical Openmx script for twin analyses that we've been employing in workshops for a number of decades now are organized. So typically we start with some comments, load all the libraries, prepare the data, and then we go into the actual model, which typically has a means component, a covariance component, that we then specify into models for MZs and DZs and combine into an overall model. Here in this session, we will focus primarily on the code and the matrices used to generate the expected covariances, because that's where the model is being defined. We, of course, then have code to run it, and a typical output will include some descriptive statistics, of course, the goodness of fit statistics of how well the model fits the data, and then the parameter estimates and their confidence intervals. So let's go into the essence of the ACE model for just the data on MZ and DZ twins. We typically use an MX matrix statement to generate a matrix that holds the additive genetic variance, the shared environmental variance, and the unique environmental variance, here referred to as VA, VC, and VE. Those are simply added up to get the expected total variance, and we can also add up the respective variance components to generate the expected MZ and DZ covariance, where the MZ covariance is A plus C, or VA plus VC, and the DZ covariance a half VA plus VC. Note that we use the names used within the matrix to then add up these variance components as one by one matrices using MX algebra statements. And the names used in the matrix are different from the names of the objects that are later used in the models that we put together. Now let's take those expectations for both the variance, which is in Cov P, and the covariance, which is in Cov MZ and Cov DZ, to combine them into our expected 2x2 covariance matrices, which have the variance on the diagonal and the covariance, the respective covariance for either MZs or DZs in the off-diagonal element. And we do that using R-bind and C-bind statements. Now we're going to add one additional thing to this basic twin model that allows us to take into account the potential effects of covariates, such as sex and age, which are typically included in the models. These would be included as covariance on the mean, and we do this by using definition variables. Definition variables are really cool, as they allow us to put the value of a particular data point into a matrix when it's being evaluated. And so it's whenever you see a data.var name in a label argument of an MX matrix, it indicates that it's using a definition variable and that that matrix element then will be dynamically updated from the dataset when the row likelihood is calculated for that particular pair of twins. So how does that translate to this particular script here? We've added both the covariates of sex and age to the intercept so that we can correct for their effects. Now we have specified both the means and the covariances. We will then put those in separate MX models that are included in an overall model called Model ACE, which is what we're going to run. That's it for a basic ACE model. Now let's see how we can build on that in a variety of ways. The first of which is we're going to add an extra sibling. As I said, we've simulated data for twin pairs, but included an extra sibling. So the question is, what would be the variance of this sibling in an ACE model? And what would be its expected covariance with either twin 1 or twin 2? And is this the same for MZ and DZ families? Here is the representation in a path diagram of this model for both MZs and DZs, which only differ in their expectation of their genetic relatedness. And now we've added a SIB and the appropriate genetic and environmental correlations with both twins. So if you use this path diagram to derive the expectations for a model when we have both twins and an extra SIB, you see that not only do we have to adjust the covariance matrix, we also have to adjust the means matrix. And of course, instead of having a 1/2 matrix, we now have a 1/3 matrix. And we, of course, need to also read in the appropriate covariates for our extra sibling. With respect to the covariance matrices, instead of a 2/2 covariance matrix, our path diagram now results in a 3/3 expected covariance matrix, where given full siblings have similar expectations in terms of their covariance to DC twins, we can basically just use the covariance for DC twins as the expected covariance between a twin, regardless of zygosity, and a sibling. Also, the expected variance for siblings is the same as that of both MZ and DC twins. So we've now just simply extended our 2/2 covariance matrix into a 3/3 covariance matrix, allowing us to also use the extra information from siblings to get more precise estimates of A, C, and E. Now, of course, when we do this in real life, we will have some families with multiple siblings and others with no siblings. But luckily, this can be taken care of by using full information maximum likelihood that assumes that for those families without any siblings, they are assumed to be missing at random. We would have to model the biggest family size and include some dummy covariates for those families with missing siblings as to include all the available data. Now, this was relatively straightforward to add one extra sibling, but maybe we can come up with an alternate parameterization that might be better suited, especially if we're dealing with multiple siblings. So think about a situation where we now have 10 siblings and we have to extend this expected covariance matrix. That would be rather cumbersome. And here we've just shown an example with just 3 extra siblings, and that is quite a bit of extra writing. So let's see if we can come up with a variation of the parameterization that is more generalizable. If we think of the expected covariance matrices, let's first focus on the genetic component, which I've color-coded here in red. And if you look at the coefficients of the additive genetic variance in this 3/3 matrix, we have taken that out and put it in a separate matrix called rel AMZ or rel ADZ, which is 1s on the diagonal and a half everywhere else except for when we're dealing with monozygotic twins. And then we have a 1 between twin 1 and twin 2. So this matrix can be specified in Openmx as a symmetric matrix with the number of variables as NTV, number of total variables. This matrix is not free, so therefore free is indicated as false. And we just provide the elements of the on the diagonal and below the diagonal as the unique elements of this matrix. Similarly, if we focus on the shared and the unique environmental matrices, you note that C appears in every element of this matrix. So in terms of the coefficients, they would all be 1, so this could be represented as a unit matrix. Similarly, the E component, now only appearing on the diagonal, could be represented by an identity matrix. So here we show all 3 matrices, rel AMZ and ADZ, rel C and rel E, and then multiply each of these relationship coefficient matrices, so to speak, with their respective variance component. And we have our new expected covariance matrix, which looks a little bit more succinct than in the case of using R binds and C binds to put together these different matrix elements. Now let's see if there is a still a better way to represent this new parameterization by taking the definition variable approach and extending it to the relationship coefficient as well. So if we go back to those rel AMZ and rel ADZ matrices, you might have noticed that there is really only a small difference between the two, and that is the expected relatedness for the twins, either 1 for the MZs or 0.5 for the DZs. But you might recall that in our data set, we actually have a variable called rel-t that is either 1 or a half. And so maybe we could just read in the actual, or no, not the actual in this case, the expected relationship between twin pairs. And then no longer have to specify two different groups for the MZs and the DZs. So here we see how we can read in this relationship coefficient for the corresponding zygosity from the data, and then reduce the script to a one-group script. Note that we have now changed the type of the matrix to a standardized matrix, which is ones on the diagonal. So we now only are reading in the relationship coefficients, the expected ones in this case, for twins and for siblings. So if we combine this with the rest of the code, we have rel-A, rel-C, and rel-E remain the same. And now our expected covariance matrix is just a one line because the zygosity is incorporated as a definition variable. We just have one group of data, one expectation, and the model or the script becomes a little bit more succinct. And so instead of reading in the ones and the 0.5s, we read in rel-t and rel-s, the expected relatedness for twins and siblings. Now, of course, these days, a lot of twin studies have gone the extra mile and also collected genotype data from their twins or their siblings. And so we could use not just the expected relatedness, but the actual relatedness. And so let's go back and have a look at our data set. And there were the three variables, rel-1,2, rel-1,3, and 2,3. And as you might expect, we simulated these to have a mean of 0.5 and a variance of a standard deviation of 0.03, which makes those actual relatednesses between about 0.4 and 0.6. So instead of using the rel-t and the rel-s, we could use this actual relatedness, rel-1,2, rel-1,3, and rel-2,3 in the respective elements of that matrix. Of course, these would typically be estimated by computing the relatedness using either GCTA or Plink and computing a genetic relationship matrix. So this script looks very similar to the previous one, where the main change really is that we now have replaced the expected by the actual relatedness, but everything else pretty much stays the same. Now, this brings us to a point where we might ask, well, do we really need MZ twins, or can we then just use DZ twins or siblings to estimate the respective genetic and environmental variance components? This was actually something that was recognized by Sarah Medland and her group, and nicely presented in a paper with first author Peter Fisher. And the synopsis of this paper shows that comparing the similarity between relatives is a function of their exact proportion of genes that they have in common, looking only within families, really provides a first validation of an estimate of the genetic variation by using a source of information that's free from the nature-nurture assumptions, which are critical for the classical twin study and have often been criticized. So this approach seems ideal to use when the equal environments assumption might be problematic for your particular variable, or when data are only available for sibling pairs. So to translate that into our scripts here, that's a fairly straightforward move. The actual model stays the same, but we now limit the data to just those of the DZs. So here we provide a quick summary of the different variations of the ACE model that we have discussed so far. The first one was just using the twin pairs and for MZs or DZ twins, so predicts a 2x2 covariance matrix. The second through the fifth script basically are different versions of the same model and should provide the same exact results, but are just different parameterizations, each of them using both MZ twins and DZ twins as well as extra SIBs, so generating a 3x3 expected covariance matrix. In the last variation, we dropped the MZs, so we're still estimating a 3x3 matrix, but only using the 1,000 DZ simulated pairs with their extra sibling. So let's see what happens to the parameter estimates across these different simulations and models. We are focusing on the left part of this graph, which was the original simulation with 1,000 MZ pairs and an extra SIB and 1,000 DZ pairs and an extra SIB. So in total, we have 2,000 trios. We used as the parameters to simulate the model that A was fixed at 0.5, C at 0.2, and E at 0.3. In the graph, you see in red the estimate of the additive genetic variance, in blue the estimate of the shared environmental variance, and in yellow the estimate of the unique environmental variance, with the light gray bars and the dark gray bars respectively indicating their lower and upper bounds, also estimated in Openmx. You'll see that for the first iteration where we just used the twin data, we get a decent recovery of the parameters that we simulated the data with. But we get a little bit of extra power by adding in an extra sibling, which you can see as the confidence intervals are a little bit tighter for the four separate scripts that we used, to including the extra sibling. Finally, when we drop the MZs from the model and just use the DZs to estimate AC and E, you notice that the estimates appear to be quite a ways off from the original estimates, but furthermore that the confidence intervals are extremely large. Because I thought this was a bit unusual, I decided to then go ahead and simulate similar data, but now extending it to 20,000 trios as well as to 200,000 trios. And you see that our estimates for AC and E are a lot closer to what we use to simulate the data when we have 20,000 trios, but our confidence intervals are still a lot wider. Once you have more than 200,000 trios down, you are perfectly fine dropping the MZs from the model. You get similar accuracy by just using the actual relatedness of DZ pairs or siblings. A quick note on efficiency. These models don't take particularly long to run. Of course, the time goes up with the amount of data available, but also goes up a little when you use the actual relatedness versus the expected relatedness. So there might still be a use to use the expected relatedness as a quicker way to get a rough estimate. So finally, what about unrelated individuals? Because I think a lot of you might actually not have data on family members, or more specifically on twin pairs. We could extend the same logic to unrelated individuals if we were able to genotype them and work out their actual relatedness. Of course, there wouldn't be any C component if these are really unrelated individuals that do not live in the same household. So we would just have an AE model. But basically, this could be extended to look not just at 2 individuals at a time, but at a whole population and work out their genetic relatedness, which is what is being done with the genetic relatedness matrices calculated from large samples of genotyped individuals. Now we can still fit the same kind of models that we've introduced here, as well as a lot of the extensions that will be covered in the later part of this session, which go into looking at the relationship, not only of the relationship between different variables, to not only focus on the causes of variation in a phenotype, but also the causes of covariation in the phenotype, and being able to figure out whether phenotypes go together because the same genes contribute. And so, in other words, they are genetically correlated or not. And so this approach is also available as part of Openmx in a new feature that Rob Kirkpatrick wrote and recently published in the special issue of Behavior Genetics that provides another range of interesting articles on structural equation modeling using twin data as well as other types of genomically informative designs to understand the causes of variation in a phenotype. Now, of course, we talked a lot about models, and it's important to remember that all models are wrong. But the practical question is, how wrong do they have to be to not be useful, which is the exact code used in the Box and Draper book published in 1986. And with that thought, thank you very much.